So, welcome everyone. Thanks for being here. This is our second doctoral meeting on aerospace, on the PhD program on aerospace science and technology. Today we're going to be discussing about propulsion and the space environment. We have 7 presentations of 7 PhD students, namely Alberto Marin, Alberto Modesti, Enrique Bello, Jesus Perales, Marco Ricardo Inchingolo, sorry for the pronunciation, Pedro José Jiménez, and Tatiana Pegotin. They are doing different PhD theses on um, electric propulsion, both numerical and experimental, and they're going to be telling us what they have done so far in the second year of their PhD thesis. The goal of these doctoral meetings is to gather together, to get to know what the PhD students are doing, for you PhD students to share your progress with your supervisors, a qualified audience in the department, faculty people, but also your peers, other PhD students, so that you can also get to know what others are doing, have discussions, and foster collaborations and exchange of ideas, which is a very important part of our research. So now, having said that, I would like to thank you all for being here.
Okay, so my thesis is focused on simulation and modeling of plasma plumes. So the plasma coming out of the thruster, and the kind of thruster are the same that Alberto Marin was talking about before. So Hall effect thrusters mainly. And my supervisor is Eduardo, and my tutor is Filippo. So first time I want to start it by giving some context, practical context of my thesis. So my research is framed inside the developing of 2 Hall effect thrusters of medium and high power from 2 different companies, Safran and Citadel. And the focus of our research group, the role of our research group in this project is mainly in theoretical and simulation contribution. So the motivation of the thesis is mainly to produce a functional 3D hybrid simulation code for simulating the Hall effect thruster plume of these 2 kind of thrusters with consistent physics and under variable conditions. Also, the prototypes, those 2 companies will give us some experimental results, and we will have to validate our results against these results provided by this company, and also investigate some phenomena occurring in them. So depending on the kind of technology that is specifically employed in these thrusters. Along with this, my research also involves some investigation of some numerical effects and phenomena that occur in the when we model the plasma plumes in certain ways. So as Alberto said before, the plasma produced by a Hall effect thruster, and specifically especially his plume, is very weakly collisional and partially magnetized, especially in the near region, near the source, the production stage. And there are various ways to simulate the plume that involve also kinetic, fluid, or hybrid methods. The code I'm working on is called EP2 Plus, and it's focused on the simulation of plasma plumes produced by various kind of thrusters in general, and it employs a model that is hybrid, particle in cell, and fluid. So heavy species, for example, neutrals and ions, are modeled as heavy species, as particles, whereas electrons are modeled as a fluid. Some of the main features of this code are that it is 3-dimensional, and it can also simulate the surface interaction with many kind of surface types via an equivalent electric circuit, and also splitting the domain in quasi-neutral and non-neutral regions in order to distinguish in order to apply properly the simplified hypothesis of assuming the density of electrons equal to the density of ions, for example. and solving better the interaction with the surfaces. The state of the art of this code is that he actually needs some better coupling with a plasma source. So the inputs of EP2 Plus are the profile, for example, the temperature profile of the or the velocity profile of the particles coming out of the thruster, and it needs a better modeling for that, and also in time-varying conditions. Other model upgrades are required for the model itself of the plume, for example, the electron fluid model or the electric circuit for better surface interaction. And other improvements are focused on the boundary condition required downstream. For example, in laboratory inside the vacuum chamber, in which we have residual pressure and wall interactions. Or in a free space in which the expansion and the cooling of the plume happens in a very different way. So regarding this, also some improvements in algorithms, for example, the kind of mesh employed has to be specifically designed for simulating very large plumes expanding in space, since we are working with medium and high power thrusters. Going into more detail for the EP2 Plus code, I already said that it models the heavy species as a particle in cell approach. For example, heavy particle collisions can be modeled in different ways. For instance, in the direct simulation Monte Carlo way, or with a deterministic scheme. And there's the code also employs population control in order to reduce statistical noise. And the part in which I'm more involved is the fluid model for electrons that currently employs continuity and momentum equations, discretized with full finite difference second order schemes. But it doesn't have energy and heat flux equation. A model at the level of heat flux equation. So the closures that the fluid model have can be, for example, isothermal or polytropic. Actually, the effect of the energy exchanges, of the heat exchanges, has been proven to be relevant in Hall effect thruster plumes. For example, here I cite research made inside our group, in which we compared the results. They compared the result between the 3D EP2 Plus code without the energy equation and the hyphen code that is two-dimensional but employs the energy equation. And we see that the effects of energy, especially in the near region of the plume, is relevant. And it is not negligible for the Hall effect thrusters. Other features of this fluid model is that the finite differences, as always, they introduce a truncation error that translates into a continuity, an error in continuity at the Dirichlet node. So if we applied a boundary condition that is in a particular node, if we applied a reference potential when we don't apply the continuity equation, all the finite difference error is gonna appear in that point, and it creates a discontinuity and some oscillation starting from that point. And we need in order to see better results, we need to have a finer mesh. So higher computational burden. Also, this kind of error translates into a convergence error, and it affects the condition number of the final matrix to be solved. And so also a limitation of the Hall parameter, that's basically the magnetization level, has to be set in order to keep the system well conditioned and reach convergence. That's all due to the kind of discretization of those equations. So after showing this context and state of the art, I can say that the research objectives, also in the frame of the projects involved, are to have a better numerical algorithms to better represent the expansion of the larger plumes in both in free space and in vacuum chambers, taking into account the magnetic fields effect and improving the existing models for surface interaction and interaction with the environment and the cooling of the plume, so the energy balance. Also, as I said before, we need an interface with the production stage that simulates better the injection condition for the plume. The methodology I'm gonna adopt is, we can say that it's modular because the main improvements can be autonomous, so the order of their implementation can be flexible, but all others will rely on each other. For example, as I will say later, the energy equation can benefit from another implementation of a different scheme to resolve the equations. Finally, with the experimental data that the company will provide, we will make a final validation of the simulation results. So, and I'm going to talk briefly about the work I've been doing this first year. So, in order to get acquaintance with the code that is very complex and it was totally new for me, I started doing some simulations in order to assess the effect of numerical diffusion in magnetized plume simulations in 3D. So the goal was to compare the two scenarios that are physically equivalent because they feature a plume with a certain angle with respect to the magnetic field that is uniform. So the two scenarios are physically equivalent but numerically different because in one scenario the magnetic field is not aligned with a mesh direction, and in the second scenario it is. So numerical diffusion occurs when the mesh is not aligned with the flux principal direction. So in order to compare these scenarios, we had to find a specific, like a distinctive phenomenon that represents the physics of a magnetized plume, and we found that in the diamagnetic behavior of the plume. So the electric current produces a diamagnetic loop inside the plume, that produces a magnetic field that is opposite to the external one. So basically, we can quantify this behavior with the Catina cross section at a certain distance from the plume injection, and compare this cross section in terms of Z component of the electric current. If this behavior is well represented in both scenarios, it means that numerical diffusion doesn't affect much the physical behavior and the representation of the plume behavior under these conditions. This study was also presented in the Space Propulsion Conference that happened in March this year. The results clearly show that the numerical diffusion, if it's present, doesn't affect much also for greater angles between the mesh and the magnetic field. Doesn't affect much the general, the global shape of the solution, and also from a quantitative point of view, the amount of current, that is flowing into these current tubes doesn't change much. So for now, we can safely say that at least for low grades of magnetization, numerical diffusion is not an issue for magnetized plume simulations. Then, in order to change the implementation of the solution of the system of equations, I started investigating a first-order approach, adopting some different schemes. First, the research was conducted in MATLAB in a 2D simplified scenario and with simplified equations. And the main results I obtained from here is that staggered approach, that the one on the right, allows us to obtain a smoother solution with also less oscillation and without the problems that happened with a full finite difference discretization. So here the scenario was a simplified one with electron current injection from a boundary and an outflow condition from the other, and a certain orientation and level of magnetic field. So the numerical, the kind of so the orientation of the magnetic field make it the current to change direction in order to reach the outflow region. And we can also see that the solution with the finite difference scheme is more irregular, and the staggered one allow us to say that is better. So at the end, we chose this second staggered approach scheme for a first order approach in order to implement it in the 3D code. And as I said before,
Alberto, sorry, you have already consumed 50. Please try to conclude as soon as possible.
Okay. So basically, the current approach employs the substitution of the continuity equation, the momentum equation inside the continuity one, and solves with a finite different approach an elliptic second order equation. We want now, with the first order method, we want to keep the equation apart and discretize them before substituting them. So we adopt the staggered approach, having the potential in the cell centers and the current in the cell phase centers, and discretize the equation in this way in order to work with the simplified matrices that have to be multiplied. This approach also was chosen because it eases the implementation of energy and the flux equation for future purposes. From preliminary results in the EP2 Plus 3D code, we see a good agreement between the full finite difference approach and the staggered approach, and also we see some improvements in the, for example, in the singularity point that you can maybe see here in the center of the domain. It doesn't show up in the staggered approach, and also some oscillation doesn't exist in the staggered approach. So some improvements and good agreement means that this approach is very promising for future applications. In order to conclude, I can say that this achievement for this first year were focused on the conference paper about numerical diffusion and research about the new numerical schemes in order to solve the equations. And the next step will involve the implementation of energy equations that will exploit the new staggered scheme, and the results will be presented in next year IEPC conference in a head-plume scenario. About the journal papers, some publications are foreseen about the Hall effect thruster scenario, but also in the staggered scheme, but also about a magnetic nozzle scenario for a helicon plasma thruster plume. So I conclude here, and if you have any question.